Hello everyone, I'm Lara from Eprosima and I will host this meeting today. As a recap, at the last meeting, Juan Víctores from the University Carlos III of Madrid delivered a presentation on the intersection of artificial intelligence and robotics. He provided a comprehensive introduction to the role of AI in robotics, highlighting its application, challenges, and potential for advancing the field. And for today, Raúl Sánchez, software engineer at Eprosima, will lead a workshop on AML IP node programming using Python API for distributed inference scenarios. We'll experience real-time image inference, where a robot captures edge image, sends them to the cloud for inference using a preloaded machine learning model, and receives actionable results. So now, Raúl's presentation.
Hello everyone, my name is Raúl Sánchez Mateos. I'm the project manager here at Proxima of the ML IP integrated platform. And today I'm going to present you how to build a scenario for distributed inference using AML IP. So the agenda for this presentation is the following. First, we'll see a very brief introduction of AML-IP and its role in distribution machine learning system. Also, we'll be talking about the ALMA project and what is the role of AML-IP within the ALMA project. Then we'll move forward with the understanding of the architecture, especially for edge and cloud components, where are the components that we are going to deploy on the edge and also on the cloud. Then we will move with the actual programming of AML-IP nodes. So we will see in detail how to create your own programs, your Python applications to work with those kind of nodes. And finally, we will end the presentation with some instruction on how to deploy the AML-IP nodes in real robots and also in cloud servers. So starting with the first point, the introduction to AML-IP and its role in distributed machine learning system, I would like to start talking about ALMA. ALMA is the project behind the AML integrating platform, and it's thought to provide a new machine learning paradigm known as AML, algebraic machine learning. This new machine learning paradigm is easily understandable by any user, so we will try to avoid the black box phenomenon of current deep neural networks. And also it will ease the interaction with humans, so we will be focusing on human AML interaction paradigms. It's also easily integrated into the current implementation of AML-IP. AML-IP will be working with many machine learning systems, but we are focusing also on providing support for AML and all the tools that we develop around algebraic machine learning in order for the user to be able to easily interact with this new paradigm. And also AML ensure long-term maintenance of AML-IP environments. And yeah, as I said before, with the AML integrating platform, we ensure that AML will be supported in the future using this kind of architecture. And this project is confirmed by 9 different partners, in which I will briefly highlight the contribution of the FKI, one of the main research institutes in Europe. Also, we count on INRIA developing the human AML interaction paradigms. Of course, Jean-Paul Foundation and Algebraic AI, which are the founders of AML technology. Then Kaiserslautern University, or RPTU now, are contributing on hardware deployments, and Fireware, BTT, and Carlos III University here from Madrid. So this is the architecture of the AML integrating platform. There are a lot of nodes, different nodes distributed on a distributed architecture and a distributed ecosystems. So, for example, let's say that on the green nodes are the AML nodes, the actual computation nodes. Then we have the red nodes, which are the agent nodes in charge of connecting all the nodes through the network. And then in the middle, we have the blue nodes, which are the nodes in charge for all the discovery process. So you can just create an independent cluster, as I show you here on the bottom right side, in which you have your own AML nodes deployed using AML IP, and you can communicate all of them just on your network or on one single device. But also, if you incorporate one agent node to the independent cluster, for example, we can see on the upper side of the image here, if you incorporate one agent node or two agent nodes here, one on each side of the deployment, you can automatically communicate different architectures, different deployments, different networks between each other. So this case will support the deployment of edge nodes on one side and cloud nodes on different devices on the clouds, and everything will be communicated through the internet. And here I have some of the main features and capabilities of the AML integrating platform. First one is that we are freeing the edge of training, so everything will be computed and calculated on the cloud. So we have the edge completely free, just reduced to its own computational effort and all the things that are strictly needed on the edge. Then the AML IP supports parallel training. You can deploy a lot of nodes, and all of these nodes will be communicating to each other, so they can cooperate to build a unique model and unique machine learning model and to create something together. Then we will provide real-time model updates. So as I said before, everything will be deployed on the cloud or even in different devices. So all of them can contribute to create a unique model, and this unique model will be accessible through any device. You can access the latest changes on your machine learning model in any case and from everywhere. Then all the data sets are private, so you can just send to any other nodes the machine learning models already computed, but you will perform all the training and computation on your local machine. So you can compute everything locally and then send out the model, and you won't be able to infer the data set used to train the model from the resulting model. So you just can share the model without sharing the actual data. And then everything, as I said before, it will create a collaborative network, so everyone gets benefit by collaborating into finding the solution, and finally the machine learning model independency. The platform can be used independently for any machine learning model, for neural networks, for AML, for random forest. So as before, the ML IP is completely independent of the machine learning model and the machine learning technology that you are about to use. For example, in this specific demo, we are going to show you how to perform inferences, distributed inference from any other device that actually happens on the cloud using TensorFlow, but you can use ResNet or you can use AML. So it's completely independent of the AML technology used. So once I finish with the brief introduction, I will move forward with understanding the architecture. Mainly, I will focus on the edge and the cloud components. So here I have the architecture that we are going to deploy in this workshop. On the left side, I have the ROS2 robot. So here on the ROS2 robot, we have already deployed the AML integrating platform, specifically some nodes of the AML integrating platform. And then on the other side, on the right side, we have the inference server. Here on the inference server, we have another nodes deployed of the AML IP, and the ROS2 robot will gather the raw data, in this case, are images. These images are sent to the inference server. The inference server will get the image, which is the raw data from the inference, then we'll transform the data in order to be usable by the machine learning model. Then we perform some computations internally. In this case, it will be inferences. And the inference is coming back to the ROS2 robot through the AML IP from the inference server until it reaches the edge device, which in our case is a ROS2 robot. And then the ROS2 robot can act according to the prediction received from the cloud. So this is what we have actually deployed. On the ROS2 robot side, we are using the ROSbot 2R from Usarion. This robot counts on a LiDAR, also an orbit camera, from which we are taking the images. And this robot already has deployed the edge node, which is the one in charge of getting the image and sending it to the inference node. And on the right side, we have our computer. Everything here will be deployed locally, so we are not handling with internet communication. This is something that we can talk about in any other working group meeting, but for now, everything will be deployed locally. So we have locally deployed the edge node and also the inference node. So there are no agent nodes specified for the communication deployed here. Everything we need is just those two kind of nodes. So as I was saying, on the laptop here, we have the inference node deployed, which will receive the image, perform the inference, and return to the edge node the already computed calculations and the results. So the results are sent back, as you can see here. The edge node will receive this kind of inference from the image, and these are the boxes of every class differentiated from the image. So we are getting the image, we are performing some kind of classification, some inference, detecting these classes on the actual image, and then we will return the coordinates of the boxes for every class, for everything that we get, or everything that we are inferencing on the image. So here is the deployment that we are going to have in the ROS2 robot, in the ROSbot 2R Usarion robot. So we have the robot, we have the camera. The camera is getting the image from the environment, and these images will be published through the camera color image raw topic using a publisher. So we have deployed a publisher, just getting the images and publishing to this kind of topic. Then also we have deployed a subscription, a ROS2 subscription, just to get the image from this topic. Then we have the AML IP edge node, which is the one receiving the images, requesting the inference to the cloud, and will receive back the inference. So once we have the reply from the cloud with the actual results of the inference, then we will publish this result we will perform some computations using these results. So for example, in this case, if we find a person on the image, then we will command to the robot here just to turn around. So if we are detecting a person with a percentage over 90%, then we will command the robot through the ROS2 publisher in command bell topic to turn around, and then we know that the robot actually show a person on the image. Okay, so we are going to continue with the deployment that we have already done on the cloud server. So let's say that our cloud server here is our computer, and we have deployed here the AMLIP inference node for performing all the inference. So you will receive an inference request and will reply with the inference solution. Here on this machine, we have already deployed the AML integrating platform just for building the AMLIP inference node. And also we are, as already mentioned before, using TensorFlow for machine learning model deployment and performing the inference. So continuing with the presentation, I will continue with the next point, which is how to actually program your nodes and how to write your Python applications using AMLIP library and deploying actual AMLIP nodes. So starting with the Edge node, the one deployed on the actual robot, I will start talking about the imports, the Python imports. So from AMLIP, we need to import several things here. The first one is the async Edge node. So we will be working with Edge node in asynchronous mode, which implies that the Edge node will get the image, request the inference, and it will continue with the execution of the program without stacking in the request inference call. So we will send the request and continue with our application. And once we receive the image, the Python application will raise a callback function. So we will be notified that the inference is ready. And also we have to import the AMLIP types for this specific use case, the inference type, which is the type that we are going to use to send the inference to the cloud. And also here we have the RCL Py import, just for importing ROS2 API. And from data types, we have the geometry messages for the twist data type, and also the sensor messages for the image usage. And here I have the code for the ROS2 nodes. On the left side, we have the subscriber image. As I said before, we are going to get the image from the Orbeck camera using ROS2 topics. So the camera will publish the image on the image topic, and here we are creating a subscriber just to connect the publisher to the subscriber and retrieving the image to be able to be used by the AMLIP Edge node. Then on the right side, we have the ROS2 publisher node, and here we have a publisher which will be publishing the twist data type. So we will be able to command the ROSbot to turn around every time that we receive an inference containing a person, or the cloud server has inference that there is a person on the image with a higher percentage than 90%. So those are the ROS2 nodes, and yeah, those are very simple nodes. And then we move forward on the actual programming of AMLIP, the AMLIP Edge node. And this is our main function on our Python application. And here you have how to create the async Edge node. This This is pretty simple. So you just need to call the async_gets_node constructor. The first parameter is the name of the node. So just setting a name that you want here. In our case, is AML async_gets_node. Then we are setting the listener, which is of type inference listener lambda. And then we specify the domain ID, just in case we want to deploy different edge nodes within the same network. We will be able to isolate this node using different domain IDs for each one. This is the ROS2 domain ID. And just focusing here on the inference listener lambda, which I have here explained, every time that we request an inference to the cloud node, this inference will be received using this function, this lambda function. So here I have on the right side, on the bottom of the right side, the inference receive definition, and the parameters of this lambda function are the actual inference, the task ID, and also the server ID that processes the inference. The task ID is just if you want to keep track of all the inference that you have been doing. So every inference or every request will be associated with that task ID. So you will be able to monitorize the progress or every time that you request a new inference. So here on the inference receive, we are just printing the server ID, the ID of the server that processed the inference, the actual inference node. Then we are printing also the inference in a string format, and we are sending this inference in a string format to the check data functions. This check data function is the only things that does is to find if there is a person on the inference. I mean, on the description, on the result of the inference, as I showed you before, there are all the boxes and all the detection of different classes. So if there is a detected person here, we'll check if this person is over the percentage of accuracy of the inference is over 80%. I said before 90%. So it's 80% on the code, and if it's above of this accuracy, then we will say that we have already found a person, and the robot will turn around. And continuing with the programming of the AML IP edge node, here you have the trace on how to request the inference to the cloud node. So this continues. This is still the edge node implementation. So if you check here, everything that I've stated here is right after the creation of this node. So continuing with the main definition, here we got the image from the subscriber. Then we are adapting the image to the format required by the AML IP. So we are creating a sequence of bytes in which we establish the byte size, the image size, and also the bytes corresponding to the image in order to be processed on the other side. And after everything, once we have the image in a sequence of bytes format, we can actually request the inference. So we use the node here, the AML IP node, to request the inference, and we send that in the inference data type format. So yeah, that's everything for the edge node. Finally, the only thing that we are doing is just printing that we have already requested the inference. As already mentioned before, this node is asynchronous. So right after requesting the inference and sending data, we'll move forward with the execution of the program, and we'll print this trace, request send with task ID, whichever task is this one, and we'll be just waiting for the inference. Then continuing with the AMLIP inference node. As before, I will start with the import names. So here, the only things that we need to import is the AMLIP PI nodes. So we are importing here the async inference node, and also for the data types, the inference solution data type. This inference node is also asynchronous, the same as the edge node, which means that we are executing our program, and once we receive the inference, we process the inference and continue with the program execution. So everything will be done asynchronously. And here we have the definition of the main function. So the same as before, we have the node created here, the async inference node, and we will need to define a name for the node, also the listener that we'll see later on, and the domain ID. Here we have to establish the same ROS2 domain ID for the edge and inference node in order for them to be automatically discovered. And once they discover each other, they will automatically start communicating. So then after creating the node, we can access to the node ID, which is the server ID that we had on the other side. And we'll start running the node. As I said before, this is asynchronous, so this run method won't stop the execution of the program. We'll just need to call the run method in order to be able for the node to create itself and start listening on the Lambda or callback functions. But this specific run function will not block the execution of the program. We are blocking the execution of the program here with a definition of a signal handler, which will pause the program. And if we receive a singing signal, will then stop the node. But for now, the program will be paused on the exit, waiting for this specific signal and not the run method on the AMLIP node. So taking a closer look here to the process inference function, which is the one that will be called every time that we receive a new inference. We have, same as before, the image that we are receiving, the task ID, and also the client ID. Once we receive the image that we have to process, which is this parameter, we are performing some conversions here. So if you remember, on the other side, we converted the image to a sequence of bytes. So we are turning it back to an image using NumPy arrays. And once we have that, we will performing the inference using the TensorFlow functions here, hub model function, setting as an input the image in an NumPy format that we received. After that, we process the inference results here. There are some more code. Everything that I've explained in here is already uploaded to the AMLIP documentation and also the AMLIP repository, so you will be able to check all the code because it's open public and everything is open source. But apart from that, once we have all the process results, all the results processed, we can continue with the response. And the response is just about to return the inference solution data type with the actual inference in a string format. That's everything that we need to do here. So that was all about how to program your AMLIP nodes. Those were pretty simple. The only thing that you need to do is to create the nodes, calling its corresponding constructor functions, and then implement the callbacks that will be called every time that you want to do something. So once we have seen the Python code, now we continue with how to deploy the AML-IP nodes in real robots and also in cloud server. So here I will explain how we are deploying everything on every machine. So starting with the Edge node, which is the ROS2 robot here, we are using Docker Compose. So every container will be everything will be running in Docker containers, and everything will start at once. So just one single command, we can deploy everything within the robot. Every container will have its own purpose, and everything will be running at the same time. So as I said, on the robot, we have already installed Docker Compose and Docker in order to run the following Docker images. For the camera and getting the image from the Astra Corver 3D camera, we have this Docker container, the Sarion Astra Campbell version, and you can find this Docker container on Docker Hub. So once you have your Docker container, your Docker Compose YAML file already created and already built, the Docker image will be automatically downloaded from Docker Hub. Then we have the ROSbot Docker image, same as before, already deployed on Docker Hub. Then the micro ROS image, also from Sarion, which has the main functionality to communicate the ROS to the ROSbot 2R with the firmware. And finally, we have the AML-IP Edge node, which is not currently deployed on Docker Hub because right now we don't have it deployed, but you can access to the Docker file that we use to create this Docker image because this is already on the GitHub repository of the AML-IP in GitHub. And yeah, you can access the Docker files, construct your own Docker image, and you will have it available on your systems. And then on the, even if here it says the Edge node, I'm talking about the and then here we have the deployment of the Inference node, which is the deployment that we have on our laptop or our PC. And the only thing that we need here is the AML IP, and that's all. The AML IP will be deployed using Docker. Here we don't need the Docker Compose framework because we are running just one single Docker image, but the AML IP inference node will be deployed using Dockers, the same as we deployed on the Edge robot. And yeah, as I said before, you have everything on GitHub. There is a AML-IP repository already available on GitHub, and you can access it and check all the code that I've been presented here. There are some parts of the code that I didn't include on the presentation, so you can go through all the Python code and check the deployment that we have already presented in this workshop. And as I said, for example, if you check here, you have the AML-IP demo nodes, then you have one specific demo for this use case, for the ROSbot 2R demo. And here you have the Docker file that you need to use for building the Docker image. And also in the README files, there are a lot of instructions to recreate all the framework. And you have also the AMLIP documentation on Read the Docs that you can go through it and check all the available nodes and everything you need to deploy your own systems. And also, I just wanted to present some other available scenarios. I've presented the one in which I have the robot and the PC or the laptop running within the same network, but of course, you can use AMLIP to deploy everything in a distributed way, in which you have the ROS robot on one network, then the inference server deployed on the cloud or any other network, and communicating everything through the internet thanks to the AMLIP agent nodes that I've been mentioned before. And this is the same use case that we have seen here, but with the deployment across the internet. Also, you can deploy not just one ROS robot, you can deploy a robot swarm. So you can have many robots, many edge devices using AMLIP and getting raw data from the environment and sending it to the cloud. And then on the cloud, you can have a collaborative training cluster or a collaborative inferencing cluster that will accept the images from the edge devices, perform the inference, and send them back to the actual robots. So yeah, that's everything that I wanted to present here. Thank you everyone for your time. And now we can move forward with the Q&A session in case you have any questions. And yeah, if not, thank you everyone. We can close the presentation here. Goodbye.
So thank you very much, Raúl. And well, that's all for today. The group will be on holiday in July and August, so see you in September. And enjoy the summer. See you. Bye.